So at the end of the class on Thursday, the thing you guys were working on was what type of energy might go in or come out of each of those technologies. So I'm going to give you some suggestions for what goes in and what comes out of each of them. At the bottom of the screen is actually a bit of a repetition of things that happen when energy changes form. And I had listed these back at the beginning when I asked you what energy is. These were things that you could look for to tell you that energy is around. So in each of those energy conversion technologies, something is going in and something is coming out. So for example, in a windmill, wind energy comes in and electrical energy could come out. Now that's not the only kind of energy that could be produced by a windmill. Did someone have a different type of energy that they listed that came out of the windmill? So it would be reasonable for you to have put kinetic energy as well. Definitely the blades are going to turn. Windmills could be used to produce electricity, but they could also be used to move gears that are going to grind something. That would be another purpose for it. The other thing that I'd like to mention is that if you put solar energy as the input, you aren't wrong. If you recall, solar energy is the original form of virtually all the energy on our planet. And in particular for wind, wind is caused by the uneven heating of our planet. And so it's the sun's energy that's causing our planet to be warm. So this is actually a pretty direct connection. But for all of these types of energy conversion technologies, technically, solar energy could come first. Now, in a hydroelectric dam, most people said, ha, that one's easy. Water energy and electrical energy are probably the input and the output, and I would agree with you. Now, water energy is a type of kinetic energy. You can't call water a type of energy. When we have a dam, and it's a hydroelectric dam, it's the movement of water through the dam that's actually causing the production of electricity. So if I were to ask you what's causing the production of electricity, don't just say water. Make sure you say that the water is moving. Movement would be the key. Now, in a gas or a coal power station, I think chemical to electrical would be a really logical conclusion. Some people would also say thermal could be the input, because when you burn gas or coal, the heat could be making things turn or move. Now I have two kinds of engines here, and we'll talk about engines again at the end of the unit. But engines don't all work on gas. Some engines could work on steam. Some of them could even be electric. And so I use the word motor there, but I guess we're really talking about the same type of technology. All three of them are attempting to make something move. So kinetic energy should probably be the output there. But in all three of them, something different is starting it. In a gas engine, I think chemical is probably the best type. In a steam engine, now here, we could put thermal, because it's hot water. Basically, in a steam engine, you make water boil, and the steam's energy is harnessed to make something move. And in an electric motor, you would have electrical energy going in so that kinetic energy comes out. Now, in a solar cell, you have solar coming in. And I would say that heat, so thermal energy or electric energy, are both very reasonable byproducts. Sometimes the sun's energy is used to warm things up. I know my husband used to build pools, and lots of people had solar pool covers. And so they would literally use the sun's energy to heat up their pool. Sometimes solar energy can be used to make electricity, like in solar-powered calculators or solar-powered watches. Now, a hydrogen fuel cell is taking hydrogen, which is a chemical substance. And generally the idea would be that we're making some sort of machine move. So you might have heard that this type of technology is starting to be used in vehicles. So I would be willing to say that we're getting kinetic energy as our output. Now you'll notice that I wrote thermal in a couple of places because thermal would be the purpose, the reason that we're doing this conversion. But realistically, I could have put thermal energy on every single example because when energy changes form, it doesn't all change exactly the way we want it. Because of things like friction, which is one of the reasons uniform motion is so difficult, usually some heat is produced as a byproduct even if you don't want it. So for example, on my smartboard projector, if you stand underneath it, it's hot. And that's because while it's making electricity, it's also producing some heat. Now this is what we had talked about on Thursday, types of energy, what energy is, energy conversions. Would anybody like to ask any questions about any of those topics? So then our goal today is going to be to talk about a couple of types of energy where we're specifically going to calculate something for them. One of them will be gravitational potential energy, and the other one will be kinetic energy. And we'll start with gravitational potential energy. So the first thing I'd like to highlight is that we are talking in this example about gravitational potential energy. But that's not the only type that is potential. On our list we made last week of types of energy, there were two other types of potential energy. There was elastic potential energy, and there was chemical potential energy. So while gravitational potential energy is the one that we will calculate the most specifically, there are two other types of potential energy that exist. So if we think about gravitational potential energy, let's think about the word potential. Any energy that's classified as potential is stored energy. So gravitational or elastic or chemical, they're all types of energy that are stored in an object. Now, why they're stored or how it got there is the thing that makes them different. In gravitational potential energy, the stored energy is due to its distance above the surface of the Earth. In other words, the work that it did against gravity. So you'll notice I use the word work here. We mentioned work in the last section. Work had to do with force and distance. So if I use a force to cover a distance, and that distance is above the surface of the Earth, then the work that I have done has given me gravitational potential energy. And so this next point here explains that idea. It takes more energy or work to move an object higher. That makes sense. If I have to go a greater distance, then my calculation for work should be a bigger number. Energy is measured in joules. So is work. Since I measure them in the same unit, they must be very related to each other. And in fact, in our examples, where we're going to assume that no energy is lost, any work that I do to lift an object up will become the potential energy of that object. So, if the object is higher, it will have more energy, and that means it will be able to do more work when it falls. So the idea with gravitational potential energy is that something is above the surface of the Earth. It doesn't have to be moving. It just has to be higher than the surface of the Earth. We'll talk about objects that are above the surface and moving in our lesson tomorrow. But for today, our goal is just to think about things that are above the surface. So this ridiculous lady that's in the picture here is sitting up on some sort of cliff. I would never do that. I don't even like standing on the top of a ladder at my own house. I have a very irrational fear of being up high. I don't know why. Is anyone else really afraid of heights? It's just me. I don't know why. I'm not afraid of blood and guts or gross things, but being above the surface where I might fall terrifies me. Anyways, the idea is that for her to get up here, she did some amount of work. Now we would calculate that by thinking about what force she needed to use and what distance she had to cover. Once she's at the top, she has potential energy. And those two values should be the same amount. So whatever work she did to get up there should be translated into potential energy for her. That means that if she were to fall and come in contact with, let's say, a rock, she should be able to transfer her potential energy to that rock and now do some work on the rock. And so the idea we're trying to convey is that we're not getting rid of any energy anywhere. We're constantly changing it from one form to another. And in this example, the work we do to get up high translates into the potential energy that the object or the person now has. So what's above here is the theory. This is how you explain what it is, what it stands for. What's below is some information about the formula and what units you're going to use. In the formula, EP stands for gravitational potential energy. Sometimes you'll even see GRAV in brackets. Now, since the type of potential energy we're going to calculate is almost uniquely gravitational, I'm not going to add extra letters there. But EP is generally the abbreviation for potential energy. In our formula, the M stands for mass. And notice it has to be in kilograms. You might recall when we talked about work, I showed you how, since work is measured in joules, joules are based on newtons, and newtons are really meters and kilograms put together. The mass absolutely has to be in kilograms. What that means is that you need to be aware that there are 1,000 grams in 1 kilogram. So if we give you a mass in grams, you will divide that by 1,000, and that will tell you how many kilograms there are. The G is really just acceleration. Now, I could put the letter A there, but since it's a specific value, we represent it with a G instead of A. The acceleration due to gravity is 9.81 meters per second squared. This is a constant, which means it has infinity significant digits. It would never be the reason that you would round off your answer. Now this value is on your formula sheet, so you don't have to memorize it. Since it's on your formula sheet, I like to remind people, if you forget what unit acceleration is measured in, look there, because gravity is acceleration, and the unit is on your formula sheet. The D is distance. It has to be in meters for the same reason mass has to be in kilograms. And what I find is that often measurements will be in centimeters, especially if we're dealing with smaller scale objects. So remember, there's 100 centimeters in a meter. Now for this one, there could be other unit conversions. If you were ever unsure, I could help you out. There's 1,000 millimeters in a meter, and then a meter is of course smaller than a kilometer. Now the idea that's key is that work can be converted to potential energy and vice versa. So if I can calculate one of the two, I should have the answer to both of them. So if I take the formula for work and I say to myself, well, force is really mass times acceleration. It's not a calculation I'm going to ask you to do individually, but if you look on your notes for work, I did mention it there so that we could see the units. Since work is really mass times acceleration times distance, it's the same thing potential energy is. Mass times the acceleration due to gravity times height specifically as a distance. But they're measured in the same units. And that's why work and potential energy could be equal to each other. Would anybody like to ask any questions about units or the formula or anything along those lines? So what I'd like to show you are a few questions that are specific to the potential energy formula, and then we'll work on some practice questions that will include that, as well as the idea of work. Sure. All right, so on the sheet that I just passed out to you, there are 3 questions, and they're to show you how to use the potential energy formula to calculate 3 different things. What I'll highly recommend to everybody is that, especially now, we have a lot of formulas involved with physics. And one of the things that people find difficult is deciding where to start. Which formula am I supposed to use? And so I think it's a very good idea with a highlighter or something, like identify which values you know. So when I look at this question, I tell myself, haha, I know the mass of that child. Now, even though something later in the question will tell me this more specifically, I can see that they're at the top of something. Anytime someone is at the top of something, or at the summit, or something that indicates they're very high up, we could assume that gravity might be involved. And so even though it's not specifically written in the question, if I can see that someone is high up, I'm going to assume that gravity might be involved in that question. Now we have the vertical height. So if I look, I have M and G and H. Now because we're talking about potential energy, we know that means we're going to use the potential energy formula. It even tells me that I am supposed to find the gravitational potential energy. Now, right now, that's the only way that you would calculate it, but by identifying the variables, we can see which formula makes sense. So to calculate gravitational potential energy, we'll multiply M and G and H. Now, this first way of using the formula is very straightforward. You are only multiplying things. I think it would be hard for you to mess this up on your calculator. We'll type in 25.0 kilograms, 9.81 meters per second squared, and 4.00 meters. Now the answer that I get is 981, and the unit is joules. Now all types of energy and work are all measured in joules. That will be the unit for all of them. So whether it's potential energy, kinetic energy, later we'll talk about mechanical energy, or work, all of them have joules as their unit. Now in this first question, that's my final answer. If I look at my original numbers, I can see that there are 3 significant digits in each of them. Notice how I'm not considering the value for gravity. The value for gravity has infinity significant digits, so I'm not ever going to think about it when I'm trying to round my answer off. I'm only going to think about my measured values, which were the mass and the height. So since they each had 3, this one has 3 as well. Now that's not the only way that you'll use this formula. Question number 2 is going to ask us not to find potential energy, but to find one of the other values in the formula. So before we go on to that question, does anyone have anything they'd like to ask about the formula? So I would like for you to do this one on your calculator with me so that I can show you something that will happen to somebody at some point, and I want to show you the difference. In this question, we have a mass. We have a number of joules, so that's the potential energy. We are looking for the bird's vertical height, so that's h. And I know anytime I'm dealing with something that's up high, the acceleration due to gravity is 9.81 meters per second squared. So I can see mghep. Okay, I'm going to use the same formula. I have all of those pieces. But this time, I'd like to calculate h. So if I look to this original formula here, if I would like h to be all by itself, I have to move m and g. My strategy would be to divide both sides by m and g. That way it'll get canceled out on the side with the h and move to the other side of the equation. So this will be my formula. So when I think about the numbers, I'm going to put 47.0 joules on the top. On the bottom, I am going to put not 800 grams, but I'm going to put that value in kilograms. Since there are 1,000 grams in a kilogram, I'm going to divide by 1,000 and write 0.8 kilograms. The value for gravity we already know is 9.81 meters per second squared. Now I'm going to pause for a second, and I want you all to do this on your calculator. So here are the 2 things I think people will come up with on their calculator. I think that either you will get 5.99 or you will get 576. One of them is right and one of them is not, and I'll show you why. Now before I show you why the one that's right is correct, I want to show you a strategy that you can use to check things. The bird is in a tree. So think about your logical knowledge of how big trees are. My answer has to be in meters because that is the unit that joules are based on. So does it make sense that a tree was almost 6 meters tall or that a tree was 576 meters tall? Now, to give you a reference, running around the track once is 400 meters. 576 would be a tree that was as tall as 1.5 times around the track, which is ridiculous if you think about how big that really is. Trees can be big, but that is an enormously big number for the height of a tree. And so using your logical brain, you could say, well, if I got 576, maybe I just want to check and make sure that I used the right numbers, that I did the right calculation, because that seems weird. So I'll tell you what happened. If you got 5.99, which is the correct answer, you remembered that when you have a fraction, what happens on the top and what happens on the bottom has to happen first before we do that final dividing. A solution would be that if you have two things on the bottom of a fraction, put them in brackets. If you do that, that will ensure that 0.8 and 9.81 get multiplied together before you do the dividing. If you just typed this into your calculator, 47 divided by 0.8 times 9.81, your calculator thought that gravity was on the top, not on the bottom. It didn't know what you were looking at. So it's really important whenever there are two things on the bottom in particular that you put brackets around them in your calculator so that your calculator knows it has to do that step first. Would anybody like to ask any questions about this particular example? So the last example here is asking you to find mass. Now to find mass, you will do something really similar to what you did for question number 2. You'll manipulate the formula. There'll be two things on the bottom of the fraction. So I'd like for you to try this third question yourself first, and then I'll show you the solution in a minute. So I'll walk you through this problem too, if you're having troubles with it. The first thing I want to do is identify what I know. 3.00 meters represents height. This number of joules is my potential energy. And I am looking for the mass, m. Now, since in this situation the hanging sign is above the ground, I know that I am probably going to use the value of acceleration due to gravity, g equals 9.81 meters per second squared. Now, since in this question I'd like to find mass, I'll refer you back to this formula here. If I'd like for mass to be all by itself, I need to divide both sides by g and h. That means g and h will get canceled on one side and end up on the other side. In other words, potential energy divided by gravity and height. And because we know from the last example, when you have two things on the bottom, you need to put them in brackets on your calculator. I'm going to add the brackets so that I don't forget. So in this example, I would do 1.47 times 10 to the power of 3 joules. And on the bottom, 9.81 meters per second squared times 3.00 meters. The answer that I get with 3 significant digits is 49.9. And my answer has to be in kilograms because that is the mass that joules are based on. So anytime you are calculating height, it will be in meters. Anytime you calculate mass, it will be in kilograms. So those units are the ones that go in this formula, and it's because that is what a joule is based on. All right, I'm going to take a couple of minutes and talk about a few of these questions. Even if you haven't done them yet, the things that I'm going to say are going to be valuable to you because they're things that you would need to think about. The first two questions didn't involve calculations, but I just want you to recognize that potential energy is something that's not moving. The object is just sitting there having the energy, and it's hard to know that there's energy if no change is happening, if nothing is moving. And because this is stored energy, it's not moving, it's not changing in any way. And with kinetic energy, if something is moving, it's really easy to see that something is happening, and it's just harder to see potential energy. Now for number 2, even though there are 3 kinds of potential energy, you really only had to choose between gravitational and elastic in this one. Elastic is any time you are stretching or compressing or bending an object, and then that object could snap back to its original spot. So think about stretching an elastic, it would snap back. Think about squishing a spring, it would pop back. Think about bending a piece of wood like they talk about bending a bow, it'll go back to its original shape. Gravitational potential energy absolutely has to do with height. If it's not obvious that the object or the person is above the surface of the Earth, then we can't say gravitational potential energy is the type. Now I wanted to point out something for number 4. In number 4, I wanted to remind you that work and potential energy can be equal to each other. In 4A, you had enough information to calculate work. You had a force and you had a distance. In 4B, you did not know the mass of the object. You could figure it out if you wanted to, but what you needed to know was that if we do work on an object to lift it up, that's now how much potential energy it should have. Now in number 5, the same thing is realistically applying. If I have a value for potential energy, I can assume that's how much work was done on the object. I'd also like to remind you that measuring something's height is the same thing as measuring distance. They're both in the same unit. So if we give you a value for potential energy, that could be the value for work. If we give the value for height, that could be the value for distance. Now the other thing that I wanted to mention, because these things repeat themselves, is over here in number 8 specifically, distance or height has to be in meters. It has to be. And a few people asked me, I only got 32 as my answer. Why do I need scientific notation? And then I asked you, did you change those centimeters into meters? And we realized immediately that was what had caused the difference in our answer. It's imperative that any time you have a distance or a height, that you use meters, not centimeters. For this whole section on energy, you have to use meters because that's what joules are based on. Now in the last one, I just wanted to show you that that was the answer before I rounded it off and used scientific notation. I could only have 3 significant digits, so I rounded it off and moved the decimal after the 2. Now for the last question, number 10, it asks you, how could you give a spring more potential energy? And I told everybody to look at the formula, and I want to focus on these 2 things. You can't change gravity. That is not a force that you are in control of. But we could adjust the mass of an object. We could adjust the height or the distance that it's going to move across. So if I want a spring to have more potential energy, I would compress it farther, or I would increase the mass. One of those 2 things would make my answer to potential energy larger.